Hello, is the desktop visible now?
Yep.
Okay, let me see. Let me get set up. Trying to get everything set up here. Okay. Um, okay. Gonna look at some. Remember, there's a new programming assignment, and we looked at that last Wednesday. And what we're going to do today is look at some code from this zip file here that has examples that are similar to the homework assignment. So we'll look at some other code, actual code that does memory accesses using virtual memory. Okay, so let's see what I do wrong. Yeah. Okay, so in the folder on paging, there's some C programs that we want to look at. Okay, so let's review real fast the demand paging idea, because that's what the homework assignment is mostly about, and that's what the examples, the code we'll look at is about. So there was this picture for demand paging that was in this folder here. Let me download that. Okay, this picture here. Okay. Okay, here's our picture. So remember, real quick, we want to talk about how a program ends up in memory. So we have virtual memory over here, physical memory over here, the memory management unit, which holds the page table here. We could think of that as a memory management unit, and then there's the hard drive. So these are the four parts and there's a CPU over here. I didn't have room to put in the picture to put the CPU. Maybe I'll redraw this later with the CPU in it, because if you add the CPU, you can add a little bit more detail. Okay, but the idea was that when you want to run a program, the program's sitting on the hard drive. It was put there by the compiler. Compilers compile your program and build the exe file. The compiler has the exe file chopped up into pages, just like virtual memory is chopped up into pages. And the compiler writes the exe file specifying which virtual pages each one of these are. So like this exe file has been specified to be page 3, page 4, and page 1. Okay, so when your program runs, the operating system, what it does to load your program is it reads the exe file, and it goes to the page table, and it goes to these pages and denotes them as valid. Okay, that's this bit here. So page 3 would be marked valid, page 4 would be marked valid, and page 1 would be marked valid. But then they're marked as not present. Nothing is loaded into physical memory until it's absolutely needed. Okay, that was the key idea. That's what we mean by demand paging. Things aren't paged into physical memory until somebody demands that they be paged into physical memory. Okay, so when your program starts up, these pages are marked as valid but not present. Then your program starts running. Okay, and we said that page 3 was the one that holds main. Okay, so when your program starts running, immediately the CPU, the program counter, is going to access that page. When the program counter accesses that page and you go over to the page table to look up where it is in memory, you find out that it's present but not valid. Okay, so this was the picture after we were done, but at this point it would be present and not valid. that throws a page fault exception telling the operating system that it needs to do something. It needs to actually copy the page into memory. So when the page is valid but not present, that tells the operating system that that page needs to be brought into a page frame. So now page 3, so the operating system picks an empty page frame. The operating system picks an empty page frame, copies that one page into the page frame. In the page table entry, it marks the page frame number as the one it chose, and then it marks it as present. So now this page table entry is kind of complete. The page 3 is in page frame 4. It's a valid page and it's actually in physical memory. Okay, so now the program counter can start executing in main. Then at some point later, the program is going to want to touch some data in the stack. When it first touches data in the stack, the first time you try to access that, now that's page 1. So you go over to page 1, and the first time you access page 1, the CPU will see that it's valid, but not present. So that throws the page fault exception, telling the operating system it has work to do. So the operating system says, okay, this page is not in memory yet. It's valid, but not present. So it goes over, so it picks a empty page frame. Okay, we said it was going to pick this one. So it picks this empty page frame. It goes over here and it takes that frame, that sector of the hard drive, copies it into that frame in memory, sets the page table entry to be pointing at that frame, and sets the present bit to 1. So now it's valid and present. Okay, now the stack accesses can go through. Okay, so now the stack access can go through and access the stack. Okay, and then the same thing can happen the first time you access the heap. The first time you access the heap, page 4 is to be present but not valid. So when it's present and not valid, that throws a page fault. The operating system has to find a empty page frame. It'll copy that. Let's see, which was that. Oh, it'll copy that page into that page frame, and then it'll mark the page table entry as that page is in that page frame. Okay, no, let's see. This one, I'm sorry, it was this one. Okay, this one is the one. This one will get marked as over there. Okay, it's confusing and it's really easy to get. You have to really fix in your mind the steps of what happens when you first access a page for the first time. Pages that are valid but not present. Okay, that causes a page fault. The operating system picks the empty page frame. The data is copied from the hard drive into the page frame. The page table entry is updated with the page frame. The page table entry is updated to be present, and then the program can continue. Okay, all right. So let's watch a program do some of this. Okay. So here's some code. I'm trying to remember which one of these is the one we want to loop. Okay, let's look at this program. This program is going to do something kind of similar to what your program assignment does. Okay, it's going to allocate virtual memory pages, and then it's going to allocate some pages, and then it's going to loop through them and touch them. Okay, and what it's going to do is it's going to write a for loop that accesses variables and well, this for loop, which does not accesses the code page. Okay, now here's what it's going to do. The program's going to start up and sleep. The sleep is actually to let us make sure we have Task Manager set up, so we can find our program in Task Manager and watch it do things. Okay. Then the program is going to access its code page. Okay. Then it's going to sleep a little bit. Okay. Then it's going to access some pages in the stack. Okay. Yeah. So what it's gonna do, it's gonna sleep, access some pages, sleep, access some pages. Okay. Now, from our picture, what that would mean is that when we would access a page for the first time, there'd have to be a page fault. Then the program sleeps and then it accesses some other page for the first time that causes a page fault. Then it sleeps and it accesses some other page for the first time that causes a page fault. So the sleeps give us time to see that the page faults happen after a little while. Okay. Now, the program's called Loop Through Memory. So I'm going to start Task Manager. Go to the details page, okay? And I'm here, I'm ready to find my program when it's running in the details page. Now I've got the page faults and page fault delta tape columns set, okay? And, okay, let me try starting the program, see what happens when we start the program. Now when we start the program, we have to find the program called Loop Through Pages. Okay, so it's running. There's Loop Through Pages. Okay, notice it's page faulting right now. See, it's slowly page faulting. There, and it stopped page faulting for a while. I think it's going to start page faulting again after a few seconds. Maybe it's already done. There, see it? Did you see a page fault? Okay. It's in the sleeps, and in between the sleeps, it does something that'll cause another page fault to happen. Okay. I think maybe it's done. So close the program and run it again just to see. Okay. There's Loop Through Memory. Okay. And you watch the page fault. There's a page fault. Now I think it's stepping through an array at this point. See, it's page faulting about once a second. I think it's stopped accessing memory and it's sleeping now. And they're page faulted again. It got out of one of the sleeps, it did a memory access, and it page faulted again. Okay, so you can actually see that these programs go through these steps of what's in this picture. The steps would be that something gets loaded into virtual memory, but as present and not valid. And then at some point you touch the page that is present but not valid, and then it actually gets page faulted into physical memory, and the page fault shows up as a statistics. Okay, all right. So now once the program has page faulted everything in, it doesn't. If it continues to touch memory, like this thing is actually forever doing the same thing. But once it's done these page faulting one time, it's never going to page fault them in again. At this point, it's done doing its page faulting. It's cycling through memory. It's cycling through this memory, but it's not going to page fault again because everything has now been allocated over here. Now, it turns out that Windows has a funny feature that you can do. You can kick pages out of memory, okay? For example, take this page here. It was this page frame, there was this sector over here. Okay, so this is a copy of this. This is virtual page 3, which got loaded into page frame 4. So virtual page 3 is loaded into page frame 4, valid and present. Windows allows you to free up that page frame. Now what that means is that bit, the present bit gets set to 0. So, and when the present bit is set to 0, this number doesn't mean anything anymore. becomes a meaningless piece of data, but Windows allows you to set that bit to 0, which essentially has freed up that page. Okay. Now, the page is still valid, but it's not present anymore. So that means that the next time you touch that page, it has to be page faulted back in. I'm not even sure why Windows has this feature that you can kick pages out of memory if you want to. Okay. They call it trimming. You're trimming your virtual memory space. You're trimming off pages from your virtual memories, from your allocated virtual memory space. It doesn't change your virtual memory space. It changes which pages are actually in memory. Okay. Now, we can watch that happen. Now, if you trim a program, it has to page fault itself back in. So when you trim, it essentially slows the program down a little bit. Like I say, I'm not really sure why Microsoft felt that this was important, but it's kind of fun to be able to do it because it lets you see virtual memory take place. When you trim a program, his present bits are all marked as 0, so nothing is no longer present in physical memory. So every time you access something in virtual memory, it's like accessing it for the first time again. It's got to get page faulted in, probably get page faulted in into a different place in physical memory, but the page table entries have to be rebuilt. Okay, so there's a program in this folder that lets us do this. Okay, in this folder is a program called Trim Pages. So let's look at the code. Trim Pages is a program I wrote to call the function that does this trim operation. Okay, the code's a little bit messy because it's doing virtual memory stuff. Okay, the actual, let's see, I'm trying to find the actual, oh, here it is. You set the working set size of a program. The working set of a program are the pages that it is got loaded into physical memory. That's called the working set, the set of page frames that it's working with. Okay. Microsoft lets programs change their working set. Okay. So you can set process working set size. Okay. So Microsoft likes to have functions that their names are sentences. So this is a function that lets you set the working set size of some other process. Okay. Okay. And we're going to set it to a minimum size. Okay. Okay. The minimum size here, I set it to be -1. Okay. So I set the minimum to, and I set the maximum to -1. If you set the working set size to -1, -1, it kicks all its pages out of memory. It makes the working set empty. So if you tell Microsoft this function to set the working size to -1, what it really does is it sets all these present bits to 0, so that the working set is 0. Okay, so this is Microsoft's way of doing this. You call the set process working set size function. You give it a handle to the process. We're going to give this function a handle to this loop through pages program that's running right now. So we're gonna trim this guy's working set. So we'll give him the PID of this process here. Okay. Now, what this program is going to do is it's going to get a PID off the command line. It's going to get the process handle from the PID. So we'll give the trim program the process ID number, which we get out of Task Manager. Okay. So from Task Manager, this program has a process ID number of 26404. So we're going to give that process ID number to the Trim Pages program. The trim pages program will translate the process ID number into a process handle using the open process function. And then it'll pass that process handle to the set process working set function to clear its working set. Okay. All right. So I've got that compiled. Okay. Now let me open a command line here. Okay. Now let's see. I'm not sure if I can get all these set up so we can watch everything happen. Okay. There's the program that's just running. That's the page we want to trim. In Task Manager, we want to watch this kind of happen. So I'm going to try to get, so there's the loop through pages program. It will not, it won't page fault anymore because it's everything, it's all loaded into memory at this point, but it's just infinitely looping through its memory. But if I trim it, then it'll need to page fault itself back in. So over here, I'll trim pages, and I'm going to trim pages of 26404. Okay, now if this works, when I run this program, we'll see this guy all of a sudden have to start page faulting again. See how he's page faulting back in? Okay, so he has, now at some point he's back to being all paged in. I think now there's a few more page faults. Now, all we did was, in a weird way, slow that program down. We didn't kill the program. We booted out of, it's actually an interesting idea. We booted out of physical memory all of his page frames. That means they had to be copied from exe file back into physical memory. When all the present bits got set to 0, then when you cycled through and got back to one of these pages, the page was no longer present, so it had to be page faulted back in. Okay. You can do it again. Let's see. It's got the same, we can just keep doing this to this program. It's, we just keep saying to the operating system, trim its virtual page, its page frame. So that means all its pages are marked as present, valid but not present, and it'll have to page fault itself back in. So, you watch that row up there, especially, if the page fault delta column is real good because it shows you the page faults in the last second. So you see that you can see how it's page faulting. This one just shows you the cumulative page faults. And you could just watch this column change. When you see this column change, you know that there are page faults happening. But sometimes I just use this column here without even using this column here. Sometimes it's just interesting to only see it's a little bit easier to see when this thing goes from 0 to non-zero than it is to see these numbers change sometimes. If you notice that there's a lot of page faulting going on in my computer, if you go like this, you can actually see. Now, see that? That's interesting. There's a program that's copying 34,000 virtual memory pages into memory every second. Okay, you wonder sometimes what your computer is doing. I don't know what that program is, but that program's kind of, I don't know if you can, I don't know what that program is offhand, but it is actually doing a lot of page faulting. That's 30,000 pages of hard drive pages have to be copied into memory every second just for that one program. Okay. Zoom, I'm running Zoom right now. Zoom is page faulting quite a bit. Zoom is page faulting 671 times a second. Okay. It's not unusual if your program acts real sluggish. One of the biggest culprits for a computer acting sluggish is that you find out that some program is page faulting like crazy. If this number hits something like 100,000 page faults a second, that'll probably start making the program act very sluggishly. Even this is probably affecting the computer a little bit. That's quite a few page faults. That may have something to do with Zoom. Because Zoom is recording the video as we go along. That's a lot of memory. And it might be that this thing's got something to do. that these are tied together and that this page faulting here might be the video being stored to the hard drive. That might be all the data that Zoom is collecting and having to store to the hard drive is being done by page faults. Okay, so Mike, let's see. Sometimes when you look at the command line, well, let's see. If I right-click this, I can ask for the properties of that program. And it's, yes, it's Zoom. Yeah, it's part of Zoom. See, that program is in the Zoom bin. It's one of the programs that come with Zoom. So that program definitely is Zoom page faulting all the video into memory, processing the video. As we're streaming, it's page fault. It's allocating pages to hold the video, and then it's copying those pages probably out to memory. Okay. Okay. So that's Zoom page faulting away. And then there are other programs that are page faulting a little bit. It's kind of normal for programs to page fault like this or like this, 10, 20 times a second. And then it's not unusual for programs to like if you watch for a while, you see every once in a while, some program will page fault a couple hundred times. Yeah, you'll just see it every once in a while, some program jumps up, does a bunch of page faults, and then goes away. That's when the program wakes up for some reason, does some operation, and it has to page fault part of its code into memory to do the operation. And then the program's done with that operation and it goes back to sleep maybe, okay? Right. If you see a massive amount of page faulting in this column, sometimes that's an indication that there's something going wrong, or that could be why your program is, a computer is acting real sluggish. Some program page faulting like crazy. Okay. Now, in our case, let's go back to, here's our program that's looping through memory. If I trim it, see, as soon as I trim it, it has to start page faulting itself back in again. Okay. So as soon as I trimmed it, there was a burst of page faulting. That would be the main body of the code. And then these are the timed page faults that have the sleep. These are the page faults that are the ones we see now are the page faults that have the sleeps in between them. Okay. When you first run this program, you'll see immediate burst of page faults. I think it's about 40. That would be the main, see, 23, 40, and then 43. So those initial bursts of page faults would be the main method, paging all the code back in. And then now this is some of the data pages that the program's paging in slowly with sleeps in between them. Okay. All right. So you can actually watch this process here. You can actually watch this process of the operating system having to find a page in physical memory, copy from the exe file into physical memory, and then set the page table entries and just do this. Every time that happens, we call that a page fault. Okay. Now, if we look at the code of this one's now, trim through pages is not really something your homework assignment will do. Trim through pages is something I thought it was just kind of interesting that it lets us watch what's going on. Notice that there's really only 3 lines of code in this program. 1 line of code gets the handle of the process ID that was from the command line. Then 1 line of code sets the working set of that process. That's the actual line of code that does what we're interested in. And then this last function just reports some statistics for us. It reports what the PID and the min and max working set sizes were. Let's see, what were those? After we trim it, we just the program will page fault itself back in, and this thing is actually reporting what it wants to be as its okay. When you call get process working set, you're finding out what the program would like its working set to be. Every program has a certain minimum and maximum number of page frames it would like to have. So when you call get process working set size, you're finding out what it would like. But this program gave it something it didn't like. It gave it -1 for min working set, -1 for max working set, which what Microsoft calls trimming its working set. So that booted all its pages out of physical memory. But then this one said this is what it would like to have. Okay, and the program would like to have. Let's see, I'm not sure what the units of that is. I don't even remember now if the units are in bytes or in pages. Okay, now if you could Google this. This parameter is a p size variable. Okay, it's a variable of type p size. Now, p size is a Microsoft type, so we have to figure out what Microsoft means by a p size type. See, does it tell us? Oh, bytes. Okay, so it's reporting bytes, not pages. It's reporting bytes. So it's telling us how many bytes of memory it would want. Okay, so these numbers are how many bytes of memory that this program wants to have as a minimum and how many bytes of memory it thinks it needs as a maximum. Okay. All right. Now, this program that's looping through memories is a little bit closer to what your homework assignment's like. Okay. So let's go through what it does. Okay. It has a constant, which is how many pages it's going to allocate. So I've set it up so to allocate 10 pages. Okay. Now, oh, uh, size is how big of an array to allocate. We want 10 pages of memory. Okay. How many bytes should 10 pages of memory be? Well, I want the array to hold ints. Every integer is 4 bytes. So I would need, for every page of memory, I need 1024 ints. So 1024 ints would be times number of pages. That's how many bytes of memory I want. Okay, that's the number of bytes of memory. That many pages times that many ints. Well, I'm sorry, that's how many ints I want. That many pages times that many ints per page is how many, that should be the size of my array. Okay, so I'm going to allocate an array of that many pages. Okay, this is going to be a pointer to the array. Okay, here's where I allocate the array. Okay, notice I'm not using free here. I'm actually doing what I'm sorry. I'm not using malloc here. This is actually what malloc does. Malloc calls virtual alloc. I'm going to use Microsoft's direct allocation. Instead of calling C's malloc function to ask for an array, I'm going to say I'm going to allocate it myself in virtual memory. So instead of allocating in the heap using malloc, I'm essentially kind of creating my own heap. I'm going to the operating system saying, allocate me some pages for my array. Okay, so in terms of this picture, instead of going in the heap and asking the C language to allocate some space for me in the heap, I'm essentially going straight to the operating system and saying, I want some pages to hold my array. Okay, my array is going to hold 1,000 ints, which is not that big, so it could easily fit in the heap, but I'm going to go directly to physical memory and I'm going to ask the operating system to allocate my array for me. Okay, so I'm going to use virtual alloc. Okay, let's see. Let's look up virtual alloc so we can look at the parameters to the function. Okay, virtual alloc takes an address, a size, an allocation type, and a protection type. Okay. Now, what I'm really trying to say is, now when I allocate memory, if we think about this picture, here's what Windows lets me do. As a running program, I can tell the operating system I want 2 pages of memory. And I can specify where they will be in virtual memory, but I can't specify where they'll be in physical memory, okay? So I can say that at this point here in virtual memory, page 5, I want one page of physical memory. So I say where in virtual memory I want to have a page that gets backed by some page in physical memory. So I'm specifying which part of the page table to put things in, but not, I'm specifying which row of the page table I'm using, but not what's going to be the page table entry, not the page frame number, okay? So this address here would be the address of where I want to allocate something. Okay, so this address here, I could say, oh, I want to allocate at this address, or I want to allocate at this address. So that lets me choose the page. Now, in this function call, I have it null. That's kind of a nice way to tell the operating system, but you pick where in my virtual memory space to put the pages. So if you're not keeping track of exactly what your own virtual memory space looks like, if you just want a page and you know you have some free space, you can make this thing null and let the operating system decide which actual empty page to fill in. Okay, so in this program, I'm cheating. Instead of keeping track of where I have free pages, I'm just going to put a null there. I'm going to let Windows decide where to put the a page. Okay. Now, in your homework assignment, you have to set where the page is. In the homework assignment, you will be specifying exactly what memory address to allocate the page at. So you'll be using this parameter here. In this case, I made it a little bit simpler by just putting null there. Let the operating system pick it. Okay. Okay. Now, the next thing is size. Now, for some reason, Microsoft didn't say the number of pages you want, it's the number of bytes that you want. Okay, so you would think that they would put the number of pages you want out. You're allocating virtual pages, so why not say how many pages you want? Well, for some reason, they decided that you would specify how many bytes you want. So then you have to translate the number of pages into bytes. Okay, so there's 4,096 bytes per page. Okay, so I'm going to have number of pages times each page that many bytes. Okay. Now then I have to specify the allocation type. Okay. Okay. I'm allocating it as reserve. Now, in Windows speak, you have to reserve memory before you can commit it. So this call is not actually the call that's going to allocate the physical memory. This call doesn't really fit into this picture at all. It's just a way of saying that some parts of my virtual memory are about to be used. It doesn't affect the page table and it doesn't affect physical memory. Microsoft just has this initial step where you have to call virtual alloc with a reserve before you can call virtual alloc with a minute commit. Okay, so we're going to call it 2 times. Okay, now actually I probably should have make this a little bit easier to read. These 2 calls are, see, here's the call that's going to reserve, and here's the call that's going to commit. Okay. When I call it to reserve, since I didn't pick the address, virtual alloc tells me where it actually did where it put it in memory. So the return value from virtual alloc is the address of where it decided to put my reserved pages. So virtual alloc reserves some pages for me in my virtual memory space. Reserving them, I mean, our textbook, for example, makes no mention of this idea of reserving. Linux doesn't do this step. It's a step that Windows, for some reason, put into their virtual memory system. That before you can actually ask for physical pages over here, you have to tell the operating system that you're reserving some memory locations over here. Okay, all right. So I call virtual alloc once to reserve. Now, in your homework assignment, reserving is one of the commands, and committing is a separate command. So there's a command for reserve and there's a command for commit. And in your homework assignment, when you reserve, you'll be given the address of where to reserve. Okay. In this case, so you won't need to you'll pass an address to virtual alloc rather than get an address back from it. Okay. So now that I know where virtual alloc reserved my pages, well, first of all, I do a little error check. If the address I get back is 0, virtual alloc failed on me. Okay, that's virtual alloc's way of saying maybe it ran out of memory. You know, maybe you don't have in this picture, maybe you don't have any free pages that you can reserve. If you don't have any free pages that you can reserve, which is not very likely because you have a lot of these pages over here, but if a program is really generating lots of data, it might fill up all its virtual memory space. Okay, so if you virtual alloc and the operating system can't find an empty spot, then they'll give you back an address of 0, so that's an error condition. Okay. Now I call virtual alloc again, and now I put the save address that it gave me because that's where I want to. Now I know the address of where I want to. The address that this one reserved is the address that I want to commit. Microsoft's committing is when it actually does this process of the committing is when you mark the thing as valid but not present. Sorry. So reserving's got nothing to do with the page table. Committing is marking it as valid but not present. So it is not yet copied into the physical memory. Okay. So this step here, committing, marks the pages as valid but not present. Okay. So, and then if something goes wrong with virtual alloc, you have to check. So if virtual alloc returns 0 again, if it should return a 0, see if it's not, yeah. In this, here I needed the actual value that it returned. Here I don't need the actual value it returns, but I need to check if it's 0 or not. So if it's not 0, it was fine. I think if it returns, if it was successful, it just gives you back that address again. So it returns the address of where it did the committing at. So that's by returning that address back to you, it's a sign that it went okay. But if it returns 0, it failed. Okay. Okay, and we are reserving the pages as read-write pages. So see, this is the command in the homework assignment. This allocation type is the command in your homework assignment, like reserve or commit. Okay, and then this is the things that say reserve it as a read page, reserve it as a write page, reserve it as an execute page. Okay, so here I'm reserving the page as a read-write page. It's a data page. It's not an executable page. It's going to be a data page because it's going to hold an array. So I mark it as read-write. Okay. Here is a list. Now, if you go down this page, what are the commands that you can give virtual alloc? And then you can give it the commit command, the reserve command. You're not going. I don't know. I don't even know what all of these do. Your homework assignment, I think your homework assignment needs commit, reserve. Oh, yeah. Your homework assignment only uses commit and reserve. And you're not going to use mem reset and mem reset undo. Okay. I've never used those myself. I'm not quite sure what they do. You can read about them. Okay. So we're going to use mem commit and mem reserve in the homework assignment. Okay. So that's the two commands that you could, the allocation types by their term. Then what are the different protections you can give? Okay, you scroll down here and you'll get a list of all the protections. Okay. Oh, and then here are the protections. Page no access, page guard. Well, actually, these aren't all of them. Oh, the actual list of all of them, you have to click on another page. Okay, so here's all of them. I'm not sure. So they have some special news here about these particular access forms, but here is the list of all the, okay, an executable page that you're allowed to read also, okay? An executable page you can read and write. An executable page you can, I'm not sure I don't know what write copy means. I haven't seen that before. I don't remember what write copy means. So it's an executable page, but write copy. Okay. Enables execute, read. Oh, copy on write. Yeah. Okay. So it's read on. So you have to be careful. This is not a writable page. This is something special. This is called copy on write. Okay. So it's a read only page. So it's like this, but it's also something called copy on write. We may talk about copy on write a little bit later. Copy on write is a very important idea in lots of places in computer science. Okay, so we might actually come back to this one later on. Okay, this is the weird one, no access. Yeah, why would you want to have allocated memory that no one's allowed to use? But Microsoft lets you do that. You can designate one of these pages as no access. That's not the same as not valid or not present. This would be a page that's valid and present, but not accessible. Okay, so Microsoft has that. I'm not sure why. Then page can be read only, read write. Again, this is the copy on write, but for a data page. This was copy on write for a code page. Okay, so you got to be careful. Write doesn't mean that you can write to the page. It's this special phrase that's very important called copy on write. Okay, and then I'm not sure what I've never used this one. I've never used that one. I don't know what those two are. Okay, your homework assignment, you're going to use, I think, execute and execute read and maybe execute read write, and no access, read only, read write. Okay, those are the ones you'll use for the homework assignment. We didn't do copy on write. Like, you're not implementing copy on write in the homework assignment. Okay, all right. So back here at the code, I reserve my number of pages. Let the operating system decide where they'll be. It tells me where they are. Then I go ahead and commit them. Now, notice I read the same size, same kind of allocation. If you can goof up by, like, suppose you allocate this as read only and you allocate this as read write, you'll get an error message then. If you reserve it as read write and then you allocate it as no, let's see, you have to, if you reserve it as read only and then you allocate it, you commit it as read write, you'll get an error message. If this thing is more, if you reserved it in a more restrictive way than you allocate and commit it, you'll get an error message. If you reserve it in a more liberal way than you commit it, you probably won't get an error message. So if you reserved it as read write and you committed it as read only, I don't think you get an error message, because read only is more restrictive than read write. Okay, but if you try to make this more liberal than this one, if you make this read only and you make this read write, then it won't work. Okay. At this point, there's page table entries, but the page table entries would then be valid but not present. Okay, so this does not create page table entries. This creates page table entries that are valid but not present. And then you have to touch the pages to actually page fault them in. Okay. Okay. So here, my address. Now, my save address. Where is it? Where did I declare save address? I've lost it now. Oh, see, it's a pointer to void. Save address is a pointer to void. Now, think about, why would virtual alloc give you back a pointer to void? Pointer to void means you don't know what you're pointing at. It's like object in Java. You just have memory. And that's exactly what we have here. We've asked the operating system to give us some memory, but the operating system has no clue what we're going to store in that memory. The operating system gives us memory as blank memory. It's not array of integer or array of strings. It's just bytes. So the operating system gives us back addresses from virtual alloc as pointers to void, okay? Now, to actually use it in my C program, I have to say what I really want it to be. I want it to be a pointer to int. So I cast my pointer to void to a pointer to int and call that the array. Now from the C languages, from the C program's point of view, that virtual memory just got allocated is an array of ints. See, this is now an array of ints. So it's the same address, but the C programming language now needs to know that I'm looking at an array of ints. Okay, so the virtual alloc returns to you a pointer to void, because from its point of view, it's just giving you essentially blank memory. Memory that you can put anything you want in it. It doesn't have a clue what you do want to put in it, so it's pointer to void. I think that what I've just allocated, no, malloc does the same thing. When you call the malloc function in C, gives you back pointer to void. Because malloc takes the same point of view. It doesn't know what you're going to really do with the memory it just gave you. So you'd say how much memory you want. Now, malloc doesn't allocate in pages. Malloc actually allocates in bytes. So malloc is real fine grained. You can ask for 27 bytes from malloc, not virtual alloc. Virtual alloc allocates pages. It doesn't make sense to ask virtual alloc for 27 bytes. Okay, if you ask it for 27 bytes, it either, I don't remember if it throws an error or if it gives you one page. I think it let's see, I think it rounds up to pages. Okay, so let's see if we can find out from the documentation what it does if you asked it for 27 bytes. Okay, so the size of the region in bytes. If the, if the LP address is null, which means that the operating system is picking where to put it, this value is rounded up to a page boundary. Okay, so it's rounded to a page size. Otherwise, oh boy, it does a really weird thing. Oh, you can. I should draw a picture. Let me try to draw. Yeah, it's interesting. Yeah, part of what you should do is read a paragraph like that and decipher it. So let's read this and see what it does. It does something kind of interesting. Let me draw a picture to. Here's my virtual memory space. I'm going to chop it up into a few pages. I'm going to chop my virtual memory space into some pages. And then we can draw kind of a picture to see what virtual alloc is doing. Yeah. Okay. So this is virtual memory. Okay. Now, suppose I do something kind of odd. Suppose suppose I that's my suppose I give virtual alloc the address that's in the middle of a page. Okay, so that's my address. And suppose my size is the equivalent of 3 pages. Okay, so my size is the equivalent of 3 pages. So 3 pages down from there, see, this would be about 1 page down from there, 2 pages down from there. Here's where I think my memory is ending. Okay. Okay. Let's see. I didn't get a nice little arrow. Let's see. Did I do that wrong? Oh, I think I know. Let's see. there. Okay, right. So I give it an address in the middle of a page, and then my size would be the equivalent of 3 pages. So there's 1, 2, 3 pages. So, think about what would be the reasonable thing for virtual alloc to give you, because it allocates pages. It would end up allocating that whole page, that whole page, that whole page, and that whole page. Okay, now let's look. Let's see what it says here. Where's okay? The size of the region in bytes. Okay, so we've allocated what would be a 3-page region, but our starting address was in the middle of a page. Okay, we're not in the null case. We're in the otherwise case. The allocated pages include all pages containing 1 or more bytes in the range from the allocated pages include all pages containing bytes in the range from here to here plus 3 pages. So that would include these bytes here. So it includes all 4 of those pages. Okay, so they do kind of a reasonable thing. If you do a weird thing like point at the middle of a page, then you think you're allocating 3 pages, you get more pages than you think. So if you ask for, now notice that means that here's another thing you might do. What if I asked actually literally for 27 bytes? Okay, if I asked for 27 bytes, I would be allocating, for example, there, and then I would have 27 bytes down to there. So then I would actually get this whole page, unless this thing happened to straddle. If this thing was right down here and 27 bytes was down here, then I might get 2 whole pages. Okay, so malloc doesn't care about pages. Malloc's much more fine grained. You can ask malloc for 27 bytes, but virtual alloc, notice that all the names are kind of the same. Malloc means memory allocation. Okay, we're working with virtual alloc, which means allocate virtual pages. So we're allocating virtual pages. Microsoft called it virtual alloc. Okay, you can't ask for 27, but you can ask for 27 bytes. You can make DW size 27 bytes, but according to this, you'll actually get you'll get whole pages. So if you do something funny like point into the middle of the page and ask for 27 bytes, you'll get the whole page. Unless you point near the end of a page and 27 bytes goes across this page boundary, you might end up actually allocating 2 whole pages. Okay. So notice that you read these documentation and they tell you what's going on. Okay. Oh, they even point out to emphasize a 2-byte range straddling a page boundary causes both pages to be allocated. Okay. So if this pointer is the last byte of that page and the size is 2 bytes, you allocate 2 whole pages. Okay. They want to emphasize that, they're emphasizing exactly what we drew in the picture, that you're going to allocate everything that straddles from the beginning to the end of your allocation. So you allocate all the pages that straddle from here to here. Okay. All right. So go back to the code. Okay. So we allocate, we reserve, then we commit. So now our pages are valid, but not yet present. Okay. Then we cast it to a pointer that C can use. We cast the pointer to void to a pointer to int. So now we can use this as an array. So we've done a very complicated way of doing a malloc call. We've essentially implemented our own malloc call. Okay. Then we go into this while loop that's going to step through the array. Okay. Okay. Notice that this thing's going to step through the array 1 byte at a time, one int at a, no, I'm sorry. It's stepping through the array here. So it's going to step through, it's going to start at the beginning of the array, and it's going to step through the array 1 page at a time. If you increase I by 1,000 ints, you're increasing your memory access by 4,000 bytes, So you're stepping through memory essentially by touching the first byte of that page, then the first byte of that page, then the first byte of that page, then the first byte of that page. Okay? So I'm stepping through memory one page at a time. And then I'm doing a 1-second sleep in between each page access. And there's 10 of those pages. Okay. Now, if we go back over here and we trim pages, that'll be the last 10 page faults we see. Okay. Because this loop, once it's page faulted the array in, that's actually where that's when these virtual pages actually get get allocated in that. Each one of these will page fault and get actually allocated in physical memory. That only happens one time. See, we're looping forever. The first time you touch those pages, they get paged in. From then on, when you touch them, there's no more page faults unless you trim the pages. Okay, so now if we go back over here, let's watch our program page fault one more time. Okay, when we trim it, we'll see a burst of page faults. That's all this code up here, page faulting in. Then we'll get down to here. There's going to be a 5-second sleep, and then we'll start stepping through the pages. Okay, and okay, there's the burst. Okay. Okay, now should be a 5-second wait here. And then we should get 10 more page faults. 25, 26, 27, 28, 29, 30, 31. Oh, we didn't get 10 more. I thought there would be 10 more. I might, yeah, I probably got something a little bit goofed up over here. There should have been 10 more after this 5-second sleep here. Well, I don't remember what this thing does. I put the comment access the code page. It's a for loop that just increments x. X is a local variable, so it's in the stack. So this would access the code in the stack, but they were accessed already up here. So they were actually already accessed because there's plenty of accessing the stack up here. But what I was interested in is this thing here that accesses the array one page at a time, and this should have been through 10 page faults. Did I miscount them? Let's see. There's the initial burst. Now this is the 5-second wait here, I think. We didn't get there isn't 10 more page faults. I mean, I don't know if I can figure out why there aren't 10 more page faults over here. Okay, there was just only a few. It seems like after this 5-second sleep, I don't know, maybe this thing's somehow screwing it up. Okay, all right, but we can see the idea that we every time things are page faulted in once. Once something is page faulted in, it stays in memory, unless somebody boots it out by this weird trim command. So when you boot it out of memory, if they are booted out of memory, then they have to get page faulted back in. So all the present bits can get set to 0. Notice that you don't actually kick these things out of memory. It's sufficient just to set these bits to 0. When you set these bits to 0, the page table has no knowledge anymore of the fact that these things are there. It still has these page table entries, but when the present bit is 0, this is a garbage value. From the point of view of the page table, that page frame number means nothing if this is not present. So if you just set these bits to 0, essentially you've kicked this all out of memory. Though the data will stay there. No, the operating system isn't going to go somehow delete these from memory. They just become pages that are not in use at that point. The data in them is the garbage data that somebody's going to see the next time. When one of these pages gets allocated to some other program, it sees garbage values in the page, and that's exactly where those values came from. They came from whatever last program had that page frame allocated to it. Okay? That's an interesting idea. Whenever you get a page in allocated to you, the data you have in it is actually the data from the previous program that used that page. It turns out that's a massive security breach, okay? In fact, operating systems don't do this anymore. For many years, when you would mark a page as in not present, it would just be free. The data would just sit in there. Then at some point, some other program would request a page frame. So that page that was freed by one program will be allocated to another program. The other program now sees the data the last program left. Okay. Well, what some clever person realized a long time ago was there's a program that reads passwords from users. That program would copy the password into a variable in memory somewhere and then process it. Eventually, that program would free that memory. Somebody wrote a program that just ran for days and just allocated pages and looked to see if there was anything that looked like a password in the page. Because every time it would allocate a page, it'd get some other program's page. Now, if it did this gazillions of times over days, literally do it billions and billions of times over days, it would occasionally get one of those pages that held a password. And there was some way that they could tell when they were looking at a page that once held a password. I forget how, but this was on an operating system back in the 80s. Okay, this wasn't Windows, but this was an operating system back in the 80s. Somebody realized that if they just ran a program on the computer forever, it would eventually it would get one of these pages that used to belong to the program that was reading in passwords. And the program could steal passwords that way. Windows now, when it allocates a page to you, it actually zeroes out the page. It actually isn't true anymore that your pages are full of garbage. They're actually, when you're given a new page, they're almost always zeroed out. Okay? And because the operating system knows that to give you a page that belonged to somebody else lets you possibly read their data. And there's a process in Windows. See all these processes that are running? One of them is the process whose job it is to zero out pages. See if I can find it. Let's see. Oh, I can't. Maybe they changed the name of it, but there was a process. There was a process. Let me see if I can find it.
I have a question.
Yeah.
So when you in your C program, when the variable hasn't been initialized and it has a garbage value, is that from your program, the garbage value?
Pardon me?
So when you initialize variables, if you just declare variables in C without a value, they have a garbage value, right?
Mm-hmm.
Is that garbage value from your program?
Probably it
From your
might, yeah,
process?
it might have to do with well, it's hard to say. Sometimes they actually don't have garbage values in them. If you actually check, you're taught that they have garbage values in them. Depending on what compiler you're using, you'll find out that sometimes they don't actually have garbage values in them. They're zero. Okay. It depends a little bit on the compiler you're using. They could be, let's see, if they actually do have a garbage value in them, it might be that that memory was used by your program earlier. Maybe when the program was loading, it might have used those variables as temporary location. Oh, for example, if it's in the stack, you get, when if you allocate a local variable in the stack, it's got garbage values that were left in the stack from the last program that used the stack. Because the stack is memory that just keeps getting used and reused and used and reused. The stack grows and shrinks and grows and shrinks. So every time you push something onto the stack, you're pushing something on a place in the stack that was used by somebody else. So if it's something like a local variable on the stack, yes, it's seeing seeing whatever value was in that stack area the last time somebody pushed something on the stack. If it's something you did from malloc, if you got a local variable by mallocing it, it's probably not garbage. Okay, unless you're mallocing an area of memory that was malloced before. Maybe malloc is recycling memory that if you do a lot of calling malloc, you may actually start recycling your own variables. Okay, so if it's a fresh page, of memory, it's probably been initialized by Windows. So if you're declaring a variable and you didn't initialize it and it's in an actual real fresh page of memory, it's probably 0 already. But if it's a new variable in the stack, it's probably seeing what was declared in the stack earlier. And if it's from the heap, it might be seeing somebody else's variable that they allocated in the heap. Okay. So so the answer depends a lot on exactly where you got the variable from. In this program here, I didn't do that actually. Now that might be an interesting thing to do. See here, we got the memory directly from the operating system. I didn't think to look what's in them. I didn't look at what's in those pages. Okay. Now, you can modify this program to print some data out of those pages. Maybe they already are 0. I would think that they're zeroed out because these were pages directly gotten from virtual alloc. My guess is they were zeroed out. I'm looking at all the process names. See if I can remember one of them being the one. And I'm not seeing, they may have changed the name. There used to be something called like page pool or no, I'm not finding it. I'll try to Google it. If I can find, yeah. If I find a reference to it, I'll make a note in the course notes. Okay, so we've run out of time. Okay, so we looked at a little bit of code that does memory accesses, and on Wednesday we'll look at some more of these code. We'll look at a couple more examples in here of a couple more examples. These programs are good examples for you to look at. The few programs in here because they do similar to things to what you're doing in your homework assignment. Little bits of what you need in the homework assignment are in these different examples or in these different page examples here. And there's also some notes here, like notes about, in this case, page classification. And I've got some notes about page virtual memory in here. So there's some notes in here that supplement the what we've been talking about in class. So we'll on Monday, or I'm sorry, on Wednesday, we'll go look at some more of these code examples, and then we'll also start talking about, the next thing to talk about is the adding the hard drive to the virtual memory page. Okay, what the beyond physical memory. Okay, we're going to start talking about the beyond physical memory, the last 2 chapters we're going to cover in the book. The beyond physical memory mechanism and beyond physical memory policies. We haven't yet started talking about those 2 chapters. Those will be the last 2 chapters that we cover. Okay. All right. So I'm going to go ahead. If you have questions, send me emails. And I'm going to see. Okay. And I'll end the class there, all right? Bye.